It's insane how you can detect pneumonia in images using deep learning models, which would save an individual's life. According to the World Health Organization, pneumonia kills around 2 million children under the age of 5 years old and is repeatedly estimated as the single leading cause of child mortality. This means that pneumonia kills more children than HIV, malaria, and measles combined. Additionally, the World Health Organization states that 95% of childhood pneumonia occurs in developing countries, more specifically in the regions of Southeast Asia and Africa. But what causes pneumonia? Bacterial and viral pathogens are the leading causes. Bacterial and viral pneumonia are treated in different manners. In terms of bacterial pneumonia, urgent care is necessary along with antibiotic treatment, in contrast to viral pneumonia, which is treated through supportive care. Thus, accurate and prompt diagnosis of pneumonia is important, and by building a CNN, we are able to analyze chest x-rays to detect pneumonia. I'll walk you through my code for this pneumonia detection. So we're going to be using a convolutional neural network, and if you don't already know what that is or what it does, I'll link a Medium article in the description, which will walk you through the process and what this kind of network does. Additionally, I'm going to link my GitHub repository below if you want to access this code. And I got this data set from Kaggle. It comes from cell.com, and if you want to learn more about it, you can go there, and I'll also link that in the description. Essentially, this data set has 5,232 chest x-ray images from children. 2,583 of them are bacterial, 1,345 of them are viral, 1,349 of them are normal, and there are a total of 5,857 patients. So let's go through the imports. First, we're going to import TensorFlow as TF. And then from tensorflow.keras.models, we're going to import sequential, which will allow us to add different layers to our model. From tensorflow.keras.layers, we're going to import dense, flattened, dropout, conv2d, and max pooling, and I'll explain how these work in my code later. From tensorflow.keras.preprocessing.image, we're going to import image data generator, which will allow us to perform augmentations on our data. And lastly, we're going to import matplotlib as PLT to do some visualization. Also, we're going to initiate our directories that we'll need for this model. So we have 3 directories. We have our training path, which has our training data, our testing path, which has our testing data, and our validation path, which has our validation data. And we also have a batch size of 10, and I like to do this because it's better to have a variable at the top if you want to change something, rather than having to search through your code if you wanted to change the batch size. Now we're going to make our image data generators, and we'll make these generators to prepare and process our images for our CNNs. So first, right away, we're going to make a pre-processing function in our image data generator, and we are going to use this model, the VGG16 model, and essentially VGG16 is a transfer learning model, and transfer learning can be used in machine learning, and what it does is reuse a pre-trained model on a new problem, and in all essence, the model exploits its knowledge from a prior task to improve generalization on a future task. Next, we're going to call the flow from directory function on our image data generator, and we're going to put our directory path in here, and we're going to reshape our images to have a dimension of 224 by 224 because we want all the images to be the same size. We're going to make sure that we specify our classes, and our classes are normal and pneumonia. We have 2 classes. And then we're going to use batch size. We're going to put our batch size as our batch size variable, which we created earlier. And then we're going to have a class mode of binary. And then we're going to do a test batch image data generator, and it's going to be the exact same as the training one, except we're going to set the shuffle to false because when we do our test batches, we don't want to have any extra augmentation on our data. And then we're going to make a validation batch image data generator, which is the same as the training batch one. And then we're going to do some visualization on our data. It's always helpful to visualize. And I just wrote some code for that here, which you can write down as well. And essentially, you'll get an image of this. And these are different types of lung images that we can get. And I showed you guys earlier in this video, but I'll show you again. For reference, we can look at the chest x-rays we have and see which ones are normal and which ones aren't normal. So this is a normal one. And then this is a chest x-ray that is not normal. And you can kind of compare it to the images that we did for visualization. It's really important to rescale your images in this project because I didn't the first time, and I actually burnt the lungs. I'll insert a picture. It was really scary, but it's very important to rescale your images. Now we're going to make our model, our actual CNN model. We're going to use a sequential, and this is going to allow us to add layers to our model, and we'll call the model. First, we're going to add a conv2d layer, and it's going to have 32 filters in a filter size of 3 by 3. We're going to use the ReLU activation, and we're going to have an input shape of 224 by 224, like we did when we reshaped our images. And then we're going to use 3 because it's the number of channels that our image has. Then we're going to have a max pooling layer, and the pool size will be 2 by 2. And then we'll have another conv2d layer, which will have 64 filters, the same filter size of 3 by 3, and the same activation of ReLU. And then we're going to have another max pooling layer, and it's going to have the same pooling size as 2 by 2. And then we're going to add another conv2d layer, which will have the same dimensions as the previous conv2 layer, and same with the max pooling 2d layer. And then we're going to have a dropout of 0.2. Now we're going to get to our dense layers, and essentially we're going to need to flatten our layers, flatten our input so it can fit our dense layers. And we're going to use the same ReLU activation, and we're going to have another dropout. And then for our last dense layer, we're going to have a sigmoid activation. And then we can compile our model, and we'll use binary cross entropy, and that's because our class mode was binary, so we should use binary cross entropy. We'll use Atom as our optimizer, and our metrics will be accuracy. And for this model, I'm going to fit my test batches because I want to see how well my model will evaluate on test data. And we'll have 17 epochs. I actually pre-ran this because it would have taken a bit of time, and I just did it to save time. But as you can see, here are all my epochs and stuff. And if we go to our last epoch, we'll notice that we have an accuracy of 99. That's almost perfect, which is great. And our loss is also looking pretty good. So yeah, this is how you make a convolutional neural network to classify images of chest x-rays for pneumonia.